This video is about infinite limits, but first of all, please don't get confused. Remember that if a function is unbounded as x approaches c, the limit does not exist. So that is not changing. Look at the graph of the function f of x equals 1 over x squared. Notice that as the x values approach 0, the value of the function is approaching infinity. So we would say that the limit as x approaches 0 of f of x does not exist. If an unbounded function means that the limit does not exist, then what is this video even about? Well, the term infinite limit simply refers to one particular way for a limit to not exist. So, infinite limits. If f of x approaches positive infinity as x approaches c from the left and from the right, we say that the limit of f of x as x approaches c is infinity. And we write it this way: the limit of f of x as x approaches c equals infinity. Please notice this does not mean that the limit exists. In fact, this is a way of saying exactly why the limit does not exist. When we say that the limit is infinity, we're saying the limit does not exist because of the unbounded nature of the function at c. Well, example 2 is déjà vu. The function f of x equals 1 over x squared is back to demonstrate our notation for infinite limits. So, first of all, let's break it down from the left and from the right. We could say that the limit as x approaches 0 from the left, that's what this little minus sign means, of 1 over x squared is equal to positive infinity. So as x approaches 0 from the left, the function increases without bound. And we could say that the limit as x approaches 0 from the right of 1 over x squared is also equal to positive infinity. In other words, as x approaches 0 from the right, the function increases without bound. When the function approaches positive infinity from the left and from the right, that's when we can say that overall the limit as x approaches 0 of 1 over x squared is equal to infinity. So saying that the limit of the function is infinity means that it approaches infinity from the left and from the right of a particular value. Let me just emphasize one more time, this still means that the limit does not exist. Saying that the limit of a function equals infinity is just telling us that the reason why the limit does not exist is because the function becomes unbounded as x approaches 0. For example 3, we have the function f of x equals 3 over x minus 2. Now, right away, we can tell that x cannot equal positive 2, because if x were 2, we would have 2 minus 2. That would be a 0 denominator, undefined. So let's see if we can analyze this numerically and find out what happens to the value of the function as we approach 2 from the left and from the right. So study this table of values for a moment. Notice that I have the x values getting closer and closer to 2 from the left and getting closer and closer to 2 from the right. So the question is, as x approaches 2 from the left and as x approaches 2 from the right, what is happening to the value of the function? So I'm looking at these y values, f of x, and I see that we have -6, -30, -300, -3000. These values are just getting lower and lower and lower. So on this side, we would say that the value of the function is decreasing without bound. It's approaching negative infinity. As x approaches 2 from the right, we see 6, 30, 300, 3000. These values are rising. They are approaching positive infinity. We would say the value of the function is increasing without bound. So here's how we would use our notation to describe this. We would say that the limit as x approaches 2 from the left of 3 over x minus 2 equals negative infinity. And for this side, we would say that the limit as x approaches 2 from the right of 3 over x minus 2 is equal to positive infinity. Because the limit from the left is negative infinity and the limit from the right is positive infinity, there's no way to combine this into a single infinite limit statement. The best we can do is to give the limit from the left and the limit from the right separately. And here's a quick peek at the graph of this function, and you can see visually that as x approaches 2 from the left, the function is approaching negative infinity, and as x approaches 2 from the right, the function is approaching positive infinity. The line x equals 2 is called a vertical asymptote. You're going to have a vertical asymptote anytime there's a value that causes a zero denominator. For example, in this case, if we do f at 2, we wind up with 3 over 2 minus 2, which gives us 3 over 0. When you have a 0 in the denominator only, that means you had a vertical asymptote. By the way, if you get 0 over 0, that does not indicate an asymptote. It probably means there's a hole. Example 4, does f of x equals 1 over 2 times x plus 1 have a vertical asymptote? Well, vertical asymptotes happen at values that cause a zero denominator. Focus on the factor of x plus 1. A constant cannot cause a zero denominator, so that's why I'm focusing on the x plus 1. If x plus 1 were to equal 0, then 2 times 0 would be 0, and we'd have a zero denominator. So this will cause a vertical asymptote. But what's x? Obviously, we would subtract 1 from both sides, and that will give us x equals -1. So x equals -1 is a vertical asymptote. And here's a quick peek at the graph of that function. Notice the vertical asymptote at x equals -1. Example 5, does f of x equals x squared plus 1 over x squared minus 1 have vertical asymptotes? Well, first of all, notice that the denominator can be factored. This is the difference of two squares, so this is going to factor as x plus 1 times x minus 1. The numerator cannot be factored. The sum of two squares, there's nothing you can do with that. So that's just going to stay x squared plus 1. By setting each factor in the denominator equal to 0, I'm going to get the vertical asymptote. So if I set x plus 1 equal to 0, that's going to give me x equals -1. Well, that is a vertical asymptote right there. On the other hand, if I set x minus 1 equal to 0, adding 1 to both sides gives me x equals +1. that's going to give me another vertical asymptote. Now, I mentioned that values that cause a 0 in the denominator only will be a vertical asymptote. So just for example, let's look at the x equals 1. Imagine that we do f at 1. What would happen? So x is 1, so that would be 1 squared plus 1. So that would be 1 plus 1, so that would be 2 in the numerator. In the denominator, I would have 1 plus 1, so that would be 2 in the first factor. And then I'd have 1 minus 1, so that would be 0. So I'd have 2 in the numerator, but then 2 times 0 is 0. So this is what I mean by you have 0 in the denominator only. That's when you have a vertical asymptote. And here's a quick peek at that graph. Notice the vertical asymptotes at -1 and +1. Example 6, does f of x equals x squared plus 2x minus 8 over x squared minus 4 have vertical asymptotes? Well, notice that the numerator and denominator can both be factored. So let's do that so we can get a better idea of what we are dealing with. So that numerator will factor as a binomial times a binomial. I see x squared, so that's going to be x times x. I'm looking at 8. When I look at 8, I'm thinking that's either going to be 2 times 4 or 8 times 1. Let's go with 2 times 4. And the middle term is 2. So let's see, if I have a -2 and a +4, that's going to turn out to be a +2. Of course, the denominator is going to factor as the difference of 2 squares. So that's going to be x minus 2 times x plus 2. All right, so vertical asymptotes are going to come from the denominator. So the two factors I should be looking at are the x minus 2, and I should also be looking at the x plus 2 very carefully. Whoops. The x minus 2 and the x plus 2. But be careful. You're going to get a vertical asymptote for a value that will cause a 0 in the denominator only. Notice that for this problem, the factor of x minus 2 appears in the numerator and the denominator. So that would actually cause a 0 in the numerator and denominator if I were to set x minus 2 equal to 0. So adding 2 to both sides, I'm talking about a value of x equals 2. So the bottom line is when you have a factor in the numerator and the denominator, that is not going to be a vertical asymptote. All right, there is a hole at x equals 2, but there's not a vertical asymptote. Okay, so watch out for that. So only the x plus 2 is going to actually be a vertical asymptote. So if I set x plus 2 equal to 0, subtracting 2 from both sides, I get x equals -2. This is my vertical asymptote. So x equals -2 is my only vertical asymptote. So let's take a quick peek at the graph and use it to review. Notice that when you have a factor that cancels out in the numerator and the denominator, that leads to a hole. So setting x minus 2 equal to 0, I got x equals 2. But notice that at x equals 2, there's not an asymptote, there's just a hole, a single undefined value. But when we have a factor that is in the denominator only, that's going to lead to a vertical asymptote. In this case, a vertical asymptote at -2, which you can see right here.